Hey guys, welcome. This is the second of 4 videos teaching you the fundamentals on how to solve second order constant coefficient homogeneous linear differential equations. And so these videos must be watched in order, must without a T, like with a silent T, because, well, if you don't watch them in order, they're not going to make as much sense to you. But of course, if you have some very basics and you know what you're doing, you may skip around and still find a lot of value. All right. Okay. But yeah, in this particular video, we're going to look at the distinct real root case, right? Because, well, in the first video, the last video, we saw that we can solve differential equations that look like this, and the specific name for them, which is kind of long, is second order linear homogeneous constant coefficient differential equation, right? Okay, so and what we said is that, like, well, if we made a guess that the solution y be equal to e to the rt, then we said that that solution will work so long as this here is true, which is that we have this quadratic equal to 0, where a, b, c here are the same as the differential equation, and the r here is, remember, in our guess, the solution y is equal to e to the rt. So the r is also very important that we figure out, in addition to knowing that a, b, and c. And obviously the a, b, and c you'll have to start in the given differential equation, because we're considering constant coefficient second order homogeneous linear differential equations. I think I just like saying that over and over. Okay, but anyway, what we said about this guy here in the last video is that it is the characteristic equation, or a characteristic polynomial, or a characteristic quadratic. Any of the three will do. Okay, cool. And so since in this case we're saying that the quadratic has two distinct real roots, it must mean that we have r1 and r2 different from each other, and that's very nice, because that automatically means that our two solutions, y equals e to the r1t and y equals e to the r2t, will form a fundamental pair of solutions, and therefore they will allow us to construct a general solution, right? And so the fundamental pair of solutions in y and y2 is guaranteed by the fact that they are distinct real roots to a quadratic. You'll see in the next video when we look at complex roots, since complex roots are distinct as they come as conjugate pairs, there too will be guaranteed a fundamental pair of solutions. It's in the final video on the one real root to the quadratic that we will have to kind of do a little bit of trickery to the fact that, like, the solution will be the same in y1 and y2, and therefore they won't form a fundamental pair, although that is not the only reason why you don't form a fundamental pair. That is, you don't need to be identical in order for you to not be a fundamental pair. Anyway, here the general solution we talked about enough in the last video, but yeah, from your fundamental pair you can construct general solution by writing it in this way. And so now let's look at a couple of examples, and that'll do us nicely for this video. Okay, so let's have this differential equation with this initial condition known. And so the characteristic equation should be easy to figure out, and it is this here, right? Now, this is a quadratic that has two real roots, and we can get to the two real roots by factoring, and this way, and there they are. So we know then that the general solution will look like this, right? One of the r's as an exponent, or involved in the exponent here, and the other r involved in this exponent. Obviously, it doesn't matter which of the exponents the 5 is on and which is on the -2. One of them is on one and the other is on the other. And of course, in the general solution, we scale them by two constants, alpha and beta, and then we add them together, right? Okay, that's how you construct the general solution from the fundamental pair. And of course, if we have some initial conditions, which we do here, we can solve for alpha and beta to get what's called the particular solution. And we saw a little bit of how that works in the first video, and so I won't labor the details, but from the general solution, we know that our y is going to look like this. And so to apply this initial condition, we could just let y equal 1 when x is 0. But to apply this, we need to find the derivative of y. Other than that, these are basic algebra details, and some that I talked about in greater detail than I needed to in the first video. So I'm not going to talk in detail about the algebra here. It's very straightforward. But yeah, basically you get here and you get there, and then you get to this, which tells you that. And using this, you can find beta now that you know alpha and betas. I went too fast then. Beta is 6/7, while alpha is 1/7. So the general solution is right here, but now that you know alpha and beta, right there and right there, yeah? Okay, so now I could move on to my final example to conclude this video. And this final example comes with 1 point, and 1 point only. Which is that given this differential equation, notice that you can't really factor the characteristic equation, and so then you'd be forced to use the quadratic formula, and no problem about that, right? And from the quadratic formula, you get these two not so pretty answers, as they involve square root of 2 and such. And so they're not as convenient, but that's not an issue. That's the whole point of this example, is that like your answers might not be integers or even rational numbers. And so they might involve an irrational number like the square root of 2, but that's not a problem. One of the r's from here clearly is -2 minus root 2, and the other is -2 plus root 2, so you throw that on. Of course, unfortunate for you, if you're given some initial conditions and you have to find the particular solution, then you might have to do some ugly like arithmetic involving square roots that I personally don't want to do, which is why this video is ending right here. Yeah, okay, cool. 2 more videos on this set of 4, and yeah, I hope you've been enjoying them, and keep watching. Lots more to learn. Take care.